Go ahead, pick up your phone, or open your laptop. The magic that's humming away inside? Well, it's the invisible engine that powers our entire modern world. And it's all thanks to a tiny sliver of silicon packed with billions of components. This is the story of the integrated circuit and how it literally built the world we live in. So here's where we're headed. We're going to jump back in time to see what life was like before the microchip to really get why it was so needed. Then we'll dig into the revolutionary idea that solved a huge problem, meet the two guys in a race to build it, and watch as computing power just explodes. And of course, we'll see how that one little chip changed absolutely everything before we peek into the future to see what's next. All right, to really appreciate the revolution, you have to understand the problem. We're talking the mid-20th century. If you wanted to build anything even remotely complex, you are up against a massive headache that engineers called the tyranny of numbers. Okay, so picture trying to build your computer, right? But every single tiny component, every transistor, every resistor is a separate little piece. You'd have to physically solder thousands, even millions of them together by hand. What you ended up with were these gigantic, power-guzzling machines that were slow and, honestly, super unreliable. I mean, one single bad connection could take the whole thing down. It was a nightmare. So the solution was an idea that sounds almost obvious to us today, but believe me, it was completely out there at the time. Someone had to ask the question, what if? What if we could build the entire circuit, all of its parts, out of one single solid block of material? And that brings us to the official definition of an integrated circuit. Now, the key phrase here is inseparably associated. That's the magic. It just means you can't take it apart. All the bits and pieces are made right there on the chip as one indivisible thing. That's what changed the game. And wow, here you can see that idea in all its glory. This isn't some schematic. It's a real photograph of a microchip. All of those intricate lines and squares, that's like an entire city of electronics, all built on a tiny piece of silicon. It replaces what would have been just a giant tangled mess of individual wires. Now, an idea this huge didn't just appear in a single eureka moment. Nope. It came to life through the brilliant work of two different inventors, working at rival companies who both saw a way to finally defeat that tyranny of wires. So first up, we have Jack Kilby over at Texas Instruments. In 1958, he pulls it off. He makes the world's very first working integrated circuit. It was made from a little piece of germanium with these tiny gold wires connecting everything. It was kind of clunky, but you know what? It worked. It proved the whole idea was actually possible. But then, just a few months later, Robert Noyce at a company called Fairchild Semiconductor, he takes the next massive leap. His design was monolithic, which is a fancy way of saying it was all one solid piece of silicon. He figured out how to basically print the components and their connections right onto the chip itself. This was the key. It made the whole thing practical to manufacture on a massive scale. And you can really see the difference here. On one side, you have Kilby's prototype. Let's say it's a little messy, but hey, it worked. On the other, a modern chip. The basic idea is the same, but it was Noyce's silicon-based method that really paved the way for the sleek, unbelievably complex designs that we use in everything today. So once this practical integrated circuit was born, it didn't just get a little better each year. No, it improved at an exponential rate. A trend so powerful and so consistent, it eventually got its own famous name. Back in 1965, a guy named Gordon Moore, one of the founders of Intel, he noticed this incredible pattern. He predicted that the number of transistors you could cram onto a chip would roughly double every 2 years. Now, this isn't a law of physics, right? It's more like a law of human innovation. And for decades, it held true, meaning our gadgets got twice as powerful for about the same price over and over and over again. And you can see that relentless progress right here. We kicked things off in the 60s with what was called small-scale integration, just a few transistors on a chip. Fast forward to the 80s, and we're at very large-scale integration, or VLSI, putting hundreds of thousands, even millions of them on there. The speed of this is it's mind-boggling. So in the beginning, we were working with just tens of transistors. Pretty quickly, that became hundreds. Then came the incredible jump to millions of transistors on one single chip. And today, we are routinely packing billions of transistors into a space smaller than your fingernail. That, right there, is Moore's law in action. So, With all this incredible, constantly doubling power, what did we do with it? Well, we basically remade the world. See, the integrated circuit isn't just another clever invention. It is the foundational technology of the last 60 years. Just think about this timeline for a second. In the 60s, NASA used these brand new ICs to build the Apollo guidance computer that took us to the moon. The 70s, we get pocket calculators and the very first microprocessors. The 80s brought the personal computer into our homes, and by the 2000s, that same basic technology let us put a supercomputer, way more powerful than anything NASA had for Apollo, right into our pockets. And it's not just computers and phones, not by a long shot. Today, from your car to your coffee maker, from your watch to your washing machine, integrated circuits are the hidden brains running pretty much everything. But here's the thing. Moore's law is starting to slow down. We're actually bumping up against the physical limits of how tiny we can make these things on silicon. So what happens next? How do we keep this incredible revolution going? Well, the next steps are absolutely fascinating. Engineers are getting creative. Instead of building circuits flat, they're starting to build them up, stacking layers in 3D. They're designing what are called chiplets, combining smaller, specialized chips, almost like high-tech Lego bricks. They're even looking past silicon to completely new materials, like graphene or, get this, even using light instead of electricity to do the computing. This kind of gives you a little peek at that first idea. You're looking at a model of a 3D chip design. See, by building vertically, engineers can make the connections between components shorter and faster, and pack way more power into the same tiny footprint. This is one of the next great frontiers in computing. You know, the integrated circuit defined the last half of the 20th century. It took us from room-sized machines to a globally connected world in the palm of your hand. So as we start to push the very limits of physics with silicon, it leaves us with this one giant, fascinating question. What's the next integrated circuit? What new invention is out there waiting to define our future?